Okay, a very good morning to all of you. So let us start this session, today's session, with we're trying to estimate physical properties of these objects. So here I've shown you images of three objects at three different wavelengths. And on the left is the star in the Orion constellation Betelgeuse. This is a Hubble Space Telescope image made at the ultraviolet wavelengths. As you know, the wavelength, the resolution is given by the wavelength divided by the size of the telescope, size of the mirror. And at the ultraviolet, it will give you slightly better resolution, so you can get a better image of Betelgeuse, which is a red giant star, as you have learned earlier. In the middle is a Cygnus A radio galaxy. This was one of the early radio sources, one of the very luminous and relatively nearby radio galaxies. It's an archetypal double-lobed radio galaxy, and it belongs to the category of what are called high luminosity radio galaxies, which are characterized by peaks of emission at the outer regions of the hotspots, which are called hotspots, and then diffuse lobes of emission. And this is the supernova remnant Cassiopeia A. By just looking at these images, that you will not be able to estimate what the intrinsic sizes are, neither would you be able to distinguish what the intrinsic luminosities are. So today we will focus on luminosity, and on another class we'll look at how sizes are estimated as well. Now, what is luminosity? Luminosity is just the energy which is generated per second. Okay, so it is erg per second in CGS units or watts in NKS or SI units. Now, even for the sun, for example, you can see that when we want to estimate physical parameters, they could actually depend on the wavelength. Here, I've just compared Betelgeuse with the sun. You can notice that Betelgeuse is actually almost 100,000 times more luminous than the sun, and it is also much, much larger than the sun. So these are parameters which you will not be able to estimate by just looking at images unless you had another handle on it, which is the distance. So we'll discuss about distance measurements as well, but that will be in another class. And today we'll focus on basic definitions of luminosity, brightness, and later, after a short break, magnitude as well. What is luminosity? It is a rate at which energy is being radiated by an object. So it is just dE dt. So it's ergs per second, or as I mentioned earlier, in watts, depending on the units that you're working with. I will switch back and forth between both, but many of the books still use the CGS units, are quite common in the astronomical literature, although one is moving more and more towards the SI or MKS units. It could be at a particular frequency, the luminosity or wavelength, in which case you would call it a monochromatic luminosity. It could be over a certain range of frequencies. For example, suppose you want to know the radioluminosity of an object, or the infrared luminosity of an object, or an X-ray luminosity of an object. Then you would integrate over a certain range of frequencies in a radio region of the spectrum, maybe from about 10 megahertz to 100 gigahertz or so, depending on the availability of observations and the range of frequencies an astronomer wishes to choose. As long as it is done uniformly while comparing different classes of objects, that should be fine. Or you may want to look at the infrared luminosities. For example, we saw infrared luminous galaxies while looking at the infrared window to observe the universe, or a certain energy range in X-rays. Then it would be over a certain range of frequencies. But in principle, you could integrate over the entire electromagnetic spectrum, in which case the word bolometric is used. So bolometric luminosity integrates over the entire range of observations of the electromagnetic spectrum, from the low energy radio waves to the high energy gamma rays. Okay, and often you'll find that there are huge gaps in the observations, but what people try and do is interpolate and calculate it. Okay, you'll notice from here that it has the same units as power, so it's the radiative output of a celestial source. As I've emphasized a short while ago as well, that the luminosity is an intrinsic property of the source. Okay, so it does not depend on distance. Flux density, what you observe, will depend on distance, but not the luminosity of the object, which is an intrinsic property of the source. Okay. Now, I've given over here the example of, again, the supernova remnant, Cassiopeia A, and which is at a distance of 3.4 kiloparsecs. We will look today at a definition of a parsec as well. It's 3.26 light years, and Cas A has a linear dimensions of about 4 parsecs. Again, to know the linear dimensions from the angular dimensions which you can measure, you have to know the distance. Cas A is the result of an explosion of a star which took place around 1680 Common Era, so it's like over 300 years ago. And I've written over here the luminosity at the radio and X-ray band. A lot of this material I've taken for this recent book by Judith Irwin, which has a slightly different approach. I will just recommend a library to get it. And it's the first few chapters, I've taken it largely from there. And I think you'll also enjoy reading the book. It gives nice examples, worked out examples as well. So you can see the radioluminosity over here. If I integrate between, this is about 20 megahertz and to about 20 gigahertz, it's about 3 into 10 to the power of 35 ergs per second. And when you look at the X-ray region of the spectrum, 0.3 to 10 kilo electron volts, it is almost 2 orders of magnitude, about 2 orders of magnitude larger. So the radial emission, which you can easily pick out that it is amongst the strongest radio sources in the sky, but it is much more luminous in the X-ray region of the spectrum compared to what you would calculate as intrinsic luminosity of source from radio frequencies. So again, underlining the importance that if you want to understand the physics of what is going on, then you would need to understand and estimate the intrinsic luminosity of the object and see how that gets related to the physical processes responsible for the emission at different wavelengths. Again, back on Cas A, I'm just trying to again illustrate to you that over here, I have given the luminosity over a certain range. This is the radio spectrum of Cas A. This is in megahertz. This is written about 10 to the power of 1, which is about 10 megahertz. Below that, it may have been possible to make these measurements. I didn't check which one it is, but it has huge errors, and that is because the ionosphere cuts this off. But in solar minimum from very specific locations, observations have been made slightly below 10 megahertz as well. And you can see that it has a non-thermal spectrum over here, which is described by power law. Okay. And if you were to calculate the luminosity, you could have actually calculated the luminosity at any of these frequencies as well, which would have given you the intrinsic luminosity of the object. But what we have quoted over here is a luminosity from about 20 megahertz to about 20 gigahertz. Okay. And here I've shown the X-ray spectrum of the source. The reason for showing the X-ray spectrum also is to illustrate to you that over here at radio frequencies in the Cas A spectrum, I see a continuum spectrum. There are no emission lines over there. But when you look at the X-ray spectrum, there are a number of emission lines as well. So when I'm calculating luminosities of the objects, I can calculate not only the continuum luminosity at any particular wavelength or frequency or energy, and also calculate the bolometric luminosity across the waveband or across the spectrum or in a particular band, the radio luminosity or the X-ray luminosity. But when I have emission lines, I also need to know the luminosity of the emission lines, because these emission lines also contain valuable information. And to do that, for example, here you can see that there is continuum emission, and superposed on it are line emissions of silicon, sulfur, etc., neon, magnesium. Now, to calculate the luminosity, what one would normally do is model the continuum and then try and estimate the line luminosities from that. So when we talk of luminosities, so far I've emphasized about continuum luminosities, but estimating the luminosities of spectral lines is also important for a whole lot of physical questions or questions that we may ask about these celestial objects. Now, when I talk about luminosity, this is just to reinforce what one has said a little while ago, that you can make observations over a certain frequency range, wavelength range, or energy range. And spectral luminosity or spectral power is what is luminosity per unit bandwidth. Okay. At the radio region, you will often find it estimated per hertz. At the optical wavelengths, the CGS units would be centimeters, but more commonly you'll find angstroms being used. A centimeter is a very large range considering the wavelengths that one is dealing with in the optical region of the spectrum. So you can calculate the luminosity per unit frequency. For example, L nu over here written as ergs per second per hertz. Similarly, you can do it for wavelengths as well. Okay. Now, the total luminosity is an integration over frequency or wavelength. And you can integrate, if this is a bolometric luminosity, you can integrate it over the entire spectrum, but you'll need different slopes at different regions, different shapes in different regions. So you'll have to take that into account. I just want to emphasize over here that when I talk about L nu as per hertz and L lambda as per angstroms per centimeter, that the values will not be the same. Total luminosity of the object, which is an intrinsic property of the source, will be the same independent of whether you integrate over frequency or integrate over wavelength. But 1 unit of frequency is not the same as 1 unit of wavelength. And that you can see very well when you write down the wavelength as lambda is equal to C upon nu, C is equal to nu lambda. That's, I just sort of put the frequency underneath. And then I've differentiated this with respect to the frequency. So d lambda d nu, this would be nu to the power of -1. So you can see it's minus C upon nu squared. So you can see straight away that if I put delta nu as 1, delta lambda is not 1. Delta lambda is equal to minus C upon nu squared. So per hertz and per frequency, the luminosities will not be the same, but the total luminosity integrated, which is an property of the radio source, will be the same. So the L nu and L lambda per unit of wavelength or frequency will be different. Now, to estimate the luminosity, what we need to know the distance. And we need to measure what is the flux or flux density of the source. So let us see how we go about doing that or defining that. And as you know, when we discussed about telescopes, we talked about measuring flux or flux density and had defined it over there. Now, if I'm talking over our energy range, then I can define dl over unit area as the flux. Okay. So, okay. But I can also define the spectral flux density, which is per unit hertz. So this would be, so luminosity is ergs per second. Okay, this would be ergs per second per centimeter squared would be the flux. But if I want to calculate it per unit of frequency or wavelength, that would be what is called flux density, spectral flux density. That becomes ergs per second per centimeter squared per hertz. Okay. For example, we talked about the Jansky, which is in MKS units, is 10 to the power of minus 26 watts per hertz per meter squared. And if you were to translate this into CGS units, it will be 10 to the power of minus 23 ergs per centimeter second per hertz per centimeter squared. You'll get 10 to the power of 7 from here in terms of converting it into ergs, but meter into centimeter will take away 10 to the power of 4. Okay, so remember that flux is not per unit of frequency or wavelength. When we talk about flux density, it is per unit frequency or per unit wavelength. Okay, and this is just expressing that in the same way. Here it was over a range. Here it is at a particular frequency. L nu is equal to F nu dA in dl lambda, F lambda, d lambda. So you can define it in both in terms of wavelength as well as frequency. Radio astronomers often do it in frequency. Optical astronomers often do it in terms of wavelength, but one has to be familiar with both. Okay. And when one tries to look at the spectrum across the electromagnetic spectrum, obviously you cannot have different units at different frequencies. So there has been more of a tendency to plot everything in terms of Jansky's across electromagnetic spectrum to look at the spectral energy distributions from the low energy to the high energy end. Okay, and this is just a flux over a certain frequency range or a certain wavelength range. When you make observations with a radio telescope, whether it be with a giant meter wave radio telescope, which I hope someday you'll be able to visit and also perhaps use at a certain later date or contribute to it, their observations are made over a certain frequency range. Your receivers are tuned to operate over a certain frequency range. And the larger the frequency range, we saw that the better is your sensitivity, but you'll have to worry about interference coming in. You'll also have to worry about the flux changing with frequency, because often you want to determine how the flux changes with frequency. So you want to not average that out. And when you want to observe at a spectral line at a particular frequency, you tune your sort of frequency range over which you're observing so that your line is somewhere within the band that you're observing. And also you have some amount of continuum emission to subtract the continuum to bring out the line emission. So that is reiterating the same thing over here. That is integral f dA. This will be total luminosity. I'd earlier written it as dL equal to f dA, but when you want to calculate the total, you integrate over the area. So luminosity is units of ergs per second. Flux is ergs per second per centimeter squared, watts per meter squared. Luminosity per unit frequency, L nu, is ergs per second per hertz. This is F nu integrated dA, and the dA which you're going to get is equal to 4 pi r squared, where r is the distance from the source to the observer. So the flux which you get per unit area will get diluted as the square of the distance, the famous inverse square law, which you are all familiar with from your undergraduate physics. So unit of flux density is watts per hertz.
What does the F in these equations stand for?
Flux.
Okay.
Yeah. Flux, if it is integrated over a certain frequency or wavelength range, and F nu if it is at a particular frequency or wavelength F lambda. All right. So F denotes the flux density over here. Flux or flux density is denoted by the italic F, and luminosity is denoted by L, and the area is dA over here. And the unit of flux density is ergs per second per hertz per centimeter squared. So this is an measurement which I can make with a telescope. Okay, the flux density is what I can estimate, and I need to know the distance to the object to be able to estimate the intrinsic property of the source, which is the luminosity of the object. And we are after intrinsic parameters because that is what is related to the property of the source itself. Because the flux density is going to vary depending upon where you are. Suppose you are measuring an astronomical object from Mars or from Earth, then obviously the flux density is going to change depending upon where you're measuring from. Or objects with the same luminosity, you're going to measure different fluxes if they're located at different distances from you. So the flux density is an observed quantity which will depend upon the intrinsic luminosity of the source and the distance between the source and the observer. Okay. This is the famous or a well-known inverse square law which you would have met in other contexts. So the 4 pi r squared term comes from basically the way the wave propagates outwards, and I will just show you a picture of it to illustrate that better. All right. Now, I just want you to think a little bit, for example, how would it vary in the case of a laser beam? Suppose it was absolutely horizontal, waves coming out in parallel. This is a very idealized case, and where there are no losses along the way. Suppose it is absolute vacuum and the rays are coming out absolutely parallel. Then will the flux change? And we have learned while looking at the radio window that the pulsar emits radiation in a certain solid angle. And when that cone hits you or passes the observer, then you see a pulse of emission. So would it also follow the inverse square law, or would it be different? Okay. While we are discussing, I want you to quietly think about that, and then perhaps you can make your suggestions in a little while, but just think a little bit about it. So here, I'm just trying to illustrate to you why the inverse square law comes up. Because as you can see, there's a source strength S, okay? And it is it's going to radiate in all directions. So effectively, what is 4 pi steradians? So the energy is going to be distributed over an area of 4 pi r squared. So as you go further and further, you can see that it is going to keep decreasing per unit area as r squared over here. This site is actually quite good to give some simple illustrations of various physical aspects. Georgia State University, and this figure I picked it up from there. You can often Google that to try and get simple concepts quite nicely illustrated in that website. Okay. So energy twice as far from the source is spread over 4 times the area, hence 1/4. Now, as you keep going further and further away, it is going to keep decreasing as 1 upon r squared, the flux density, which you measure per unit area. So in a way, inverse square law is a statement of the conservation of energy. Suppose you imagine 2 spherical surfaces of radius r and r1 around an isolated star. Then basically, if at r1, 4 pi r1 squared is equal to fr 4 pi r squared, so r and r1. And if we want to consider r1 to be fixed, then fr, which is vary as 1 upon r squared, and it is basically conserving energy over here. Flux per unit area multiplied by the area, that is a constant quantity. Now, we have so far talked about observations. When you observe with a telescope from the Earth, and you're talking about detecting the energy which is coming from a celestial source, whether it be the sun or whether it be any other object, whether it be a supernova remnant or a radio galaxy. And we saw that the flux density which you observe is inversely proportional to the square of the distance. So that once you can estimate the distance, you can get the luminosity, which is an intrinsic property of the source. I can also consider the astrophysical flux at the surface of a star. For example, the sun itself. Sun has a certain radius r, okay, and it has a certain luminosity. So I can relate that to L star, which is the luminosity of a star, okay, is the flux at the star, is the astrophysical flux at the star, multiplied by 4 pi r star squared. So the energy per unit area is the flux coming out of the surface of the star. And if I multiply this by the total area on the surface of the star, okay, then I will get the luminosity of the objects, right? So if this is ergs per second per centimeter squared, then if 4 pi r star squared, if I put it in centimeters squared, I'll get a luminosity in terms of ergs per second. I can relate this to fr at any distance, fr 4 pi r squared, and then I can get the flux at any distance, which should be the ratio of the radius of the star to the distance at which you're observing it multiplied by the flux at the surface of the star. So the flux at the surface of the star is an important physical quantity. Now, I'll give you a little break because you didn't do any of the sums last time. So, except Ahan and Kamakshi. So I just want you to take 5 minutes. Using these parameters, you can do it very simply and think a little bit about the questions I asked you about how it might change for a pulsar and a very idealized laser beam. Okay, laser beams, I'm talking of a very idealized laser beam where the beam is absolutely parallel, okay, and there are no losses along the way. I've given you expressions for the sun's luminosity, radius, and the Earth-Sun distance, okay, which is 1 astronomical units. I've given you mixed up the units. Okay, this is kilometers, this is kilometers, this is ergs per second. Okay, and I want you to calculate the astrophysical flux on the surface of the sun in CGS units. Estimate the flux of the sun at a distance of 1 AU, which is our sun, which is our distance from the sun. And this quantity is referred to as the solar constant. And I also want you to calculate what fraction of the solar flux is intercepted by the Earth. Okay. Hi, everybody. So would you like to share your answers? Anybody?
For the star's luminosity at its surface, the thing I initially calculated 6.3 times 10 to the power 20, but I think that's because I forgot to count that the radius is in kilometers and shouldn't, is flux in CGS units, is it per kilometer squared or per meter squared? I couldn't remember.
See, you'll have to convert it to kilometers to centimeters to be in the CGS units.
When I'm converting it to centimeters, I'm getting 6.3 times 10 to the minus 70.
For what is that? Which one?
For the first one, astronomical flux, astrophysical flux.
Okay, for the first one, what you would get is, okay, let's just go through. I think I probably have the answers in the next sheet, but I'll tell you what the, yeah, go ahead. Anybody else?
I actually converted it to centimeters, the radius of the sun, before I did the rest of it. Yeah. And I got 6.3 into 10 raised to 13, 13.
13, is it?
Yeah.
Okay. Okay, okay, that is closer than the others, but I still think
if you convert from kilometers to centimeters,
yeah,
wouldn't it be 6.3 times 10 to the power 10?
Yes, that is the right answer. That's the right answer, I think. Okay, no, that's because what you have is 3.85 into 10 to the power of 33. That's the luminosity divided by 4 pi r squared. R squared is 6.96 into 10 to the power of 5 kilometers. That will become 10 to the power of 10 centimeters, right? Because 10 to the power of 3 to convert it to meters and 10 to the power of another 2. So that will become 10 to the power of 10 centimeters. So then if you square that, you will get, see, 33 on top and then 20 at the bottom and 3.8, whatever, 3.84 or so. And if I multiply that by 100, that becomes 10 to the power of 31. And I divide that by 4 pi r squared, 6.955 squared multiplied by 4 multiplied by 5. That gives me 6.33 into 10 to the power of 10 ergs per second per centimeter squared.
Yes, so that's correct. I forgot to write down the decimal when I wrote the sun's luminosity.
Okay, excellent. Okay. Now estimate the flux of the sun. Actually, it is important to keep track of these units, you know, and that is why I was trying to get you all. These are very simple sums, but often one goofs in the units. You know, that is the main problem that one has to be careful about. Estimate the flux of the sun at a distance of 1 AU in CGS units. Has anybody tried that? It'll be the same. Sorry, go ahead. Who is this?
Yeah, just a second, sir. I'm just double checking my decimals because you need to use the earlier answer for this, right?
Okay, sure.
So I'm just double checking that.
Sure.
Sir?
Yeah, hi.
Hello, sir. So I get the answer 1.36 into 10 to the power 10 for the second one.
10 to the power of 10. 1.36 is right, but 10 to the power of 10, I think you've mixed up the units somewhere.
Sir, is it 1.36 into 10 to the power 2?
Erg per second per centimeter squared.
Yeah, ergs per second per centimeter squared.
That's not what I'm getting. Okay, just look at the top again. On the numerator would be the same luminosity of the sun in CGS units, suppose 3.8408584 into 10 to the power of 33, right? And then at the bottom would be 4 pi multiplied by 1.496 squared into 10 to the power of, this again is 10 to the power of 8, this will become 10 to the power of 13.
Yeah.
So that will become 10 to the power of 26. Okay, 10 to the power of 26. Now on the top, if I make it 385 to make the division a bit simpler, then I'll get 385 into 10 to the power of 31, right? 31 divided by 4 pi into 1.496 squared into 10 to the power of 26. So 10 to the power of 31 minus 10 to the power of 26 will give me 10 to the power of 5. And this 385 divided by 4 pi and 1.496 squared gives me 13.69 into 10 to the power of 5. So that gives me 1.369 into 10 to the power of 6 erg per second per centimeter squared.
Yes, I corrected that and I got the exact same answer.
Okay, who's this? Sorry?
Ananya.
Ananya, okay, excellent. Okay, so excellent, Ananya. So again, I think it's just, I mean, it's not it's conceptually all of fine, but it's just a question of trying to make sure the units are okay. Now, the third question is, what fraction of the solar flux is intercepted by the Earth? You can put it as pi, the radius of the Earth squared. So it is pi r squared, where r is the radius of the Earth, divided by 4 pi capital R squared, say, which is the distance between the Earth and the Sun. And if you do that sum, can do it later, you should get 4.5 into 10 to the power of minus 10. So it is a very small number, right? A very small number. So a very small, tiny fraction that gets intercepted by the Earth. There's something called a Dyson Sphere. So look that up and see what Dyson Sphere means, okay? We'll not discuss it right now. Just leave it to you to find out what a Dyson Sphere is. So these are the answers which I've written down over here, okay? Now, let me ask you just a question as to what you think. This is actually extremely important number, okay? And here we have got a slightly higher value than what you normally meet in the literature because you've taken the total luminosity of the sun. But people would actually make these measurements in a certain sort of with the visual range and within a certain range. So you may get a slightly smaller value than that. Okay. Now, this is the amount of energy which you're receiving from the sun per unit area. Okay. Solar constant. And this is really the important thing for which drives our climate, and life itself is sustained on the amount of energy we receive from the sun. So this is the energy per unit time, per unit area. Okay. And you can express this in NKS units as well, or SI units. Now, let me ask you a question. Do you think the solar constant is a constant? The amount of flux that you receive from the sun remains a constant?
No.
No. Why?
Because the sun's surface is like a very dynamic process going on there. So the amount of flux leaving the sun it'll vary from time to time. Like I think just a few days ago, there was also another coronal mass ejection. So, and I think stuff like that would influence the solar constant.
Okay, that's a good first answer. Do you think there would be some systematic variations? Any one of you, Ahan, or any one of you?
I've heard that our sun is unusually quiet, and that over long periods of time, its output hasn't really changed by more than like 10%, compared to smaller stars, which have a much more highly variable power output.
Yeah, that is true, that our sun is nearly constant, but not quite constant. And many stars are far, far more variable than the sun. Akino, that's absolutely correct. What I'm asking is there any, both of you have talked about small variations for the sun. Is there any systematic variation? Because the systematic variation will also affect the amount of flux that we receive.
Well, our orbit around the sun is slightly elliptical, right? So when we're further away, we'll get slightly less flux.
Yeah, but, because of the processes, the nuclear processes happening on the sun, uh, as it runs out of fuel, are we experiencing a decrease in the solar flux?
Actually, the thing is that we will look at long-term evolution of the sun because the sun's luminosity has also changed. This is on a much longer time scale. That will happen, and that is happening. That is the evolution of the sun on billions of year time scales. That since the sun was first born to what it is today, we will look at how the radius and the luminosity has changed. But I was going to something much more sort of straightforward, which is that it just depends on the solar activity. But the solar activity is, as you know, can be measured from the sunspot number, right? And the sun has a 11-year cycle over here, and you can see that this is the solar irradiance which has been measured. This Greg Kopp, he actually maintains a very regular website. You can see this figure was updated as recently as 6th of October. So I sort of picked this up from his website just this morning. And you can see the variations of the solar irradiance. This is plotted from about 1980 and goes on till today. We are just getting out of a solar minimum, okay, and getting into, just getting out of it. And you can see the close correlation between the sunspot numbers. So the solar cycle, the irradiance, the solar irradiance, or the amount of flux that we receive from the sun varies with the solar cycle. When the sunspot number is larger, the solar flux is also larger. That you can see over here that if you look at the average value over here, okay, and you see by how much it has varied, it will be less, within about 0.1%. But we learned while looking at the radio window that at the radio window, the radio flux density can vary by very large amounts. When the bursts happen, it can, active sun is several orders of magnitude higher flux density than the quiet sun at radio frequencies. But the radio frequencies carry very little energy, but the flux densities can vary by large amounts. So remember that the solar, although it's called a solar constant, is not really a constant. Okay? It varies with the sunspot cycle. I sort of wanted to show you this picture of this to illustrate how luminous the sun is actually. One should not take it as a message that we are consuming so little energy so we can consume more, because even the amount, unchecked consumerism has resulted in devastating effects on our planet. This is the global primary energy consumption, and they have actually breaking it up into different sources. And you can see renewable energy is still a tiny little chunk over here. Okay, solar, wind, hydro, and a lot of it is just gas, oil, and coal, the fossil fuels. And this is the amount of energy, 1 terawatt hour, that is 10 to the power of 12 watts for 1 hour, which will translate into 3.6 into 10 to the power of 15, which is just multiplying it by 3,600 seconds in an hour, joules. And 160,000 terawatt hours is the consumption in 1 hour in 2019. It will probably be a bit more today. And the sun's energy emitted in 1 hour, I've just taken the luminosity in MKS units to compare with this, into 3,600 seconds, that's 1.38 in 10 to the power of 30. So you can see that even at a peak, we are the amount of energy we consume. So you can imagine the whole world, the global primary source, all the industries, trains, planes, and you name it, everything. We are still a tiny minuscule that the sun is generating. So this only is a message to illustrate how luminous the sun is. And it is not a message that you should consume more, but one should continue to consume less and try and save our planet. And the sun is a very ordinary star. So just to give you an idea of the kind of energies that one is dealing with when one is talking about celestial objects. Now, let me sort of go back to the questions that we raised. So what about a laser beam and what about the pulsar? Did any of you think a little bit about that?
Teacher, so for a pulsar, even if the area it's emitting in is smaller, it's still growing proportionally with the square of the distance as it travels through space. So even though it doesn't have the 4 pi r squared formula, it will still, the flux density will still decrease with like an inverse square law. Before a laser whose area does not groove through space, if it's like a perfect laser, all light rays parallel, its flux density won't change if it's a perfect laser.
Okay. Okay, thank you, Akino. Anybody else? Okay, what he's saying is correct. Okay. Now, how would it vary in the case of a laser? I'm talking of an ideal where there are no losses and the rays are parallel, then the flux would be a constant. Because you can see that luminosity is integration of FdA, okay? And your area is a constant, so your flux is going to be constant. But a diverging laser beam with a constant opening angle, which is similar to that of a pulsar with a cone which is opening out with a certain solid angle cone, then it will decrease as 1 over r squared. You can think of this as, for example, if you go back to this equation, although I've written this for a particular frequency, it doesn't really matter. You can think of luminosity as the integral of flux into dA, right? All right. Now, in the case of the inverse square law, when we are talking about the celestial sources, it is 4 pi r squared, and that is what is going to come out over here, right? So flux would be L nu upon 4 pi r squared. Now, suppose it had a constant opening angle, okay? Constant opening angle. What you could do is you could take the flux out because they are supposed to flux, okay? F, it will be integral dA, which is effectively A, okay? And what is A? When it is opening at a, when it is coming out with a constant solid angle, then solid angle is defined as omega is equal to A upon r squared, isn't it? Isn't it? So you'll get flux into omega into r squared. So your flux will go down as r squared, but you have to factor omega over there, not 4 pi. 4 pi would be if emission is in all directions. So you'll have to, if you just apply the 4 pi r squared formula without looking at the solid angle, you will get a wrong answer. But once you know the opening angle, whether it be a diverging laser beam or it be a pulsar radiation, then once you know the opening solid angle, then you can go and make your calculation and you'll get the right answer. So it does vary upon 1 upon r squared, but you'll have to be careful about the opening angle.